It's very convenient to have stock solutions in the stock room. A stock solution is a more concentrated solution of a chemical that you might need, like sodium chloride or sodium hydroxide or hydrochloric acid. And then when you use it, you dilute it. It's a little bit like going to the grocery store and buying frozen orange juice concentrate, right? You can't drink that stuff. It's way too sweet. But it's convenient because it takes up a lot less space in the freezer. And so you have these little cans of orange juice, and you come home and you put them in your freezer. Then when you go to use them, you dilute them, right? You take that can of orange stuff, orange goodness, and you pour it into a pitcher. Sometimes you have to convince it to come out. It goes thunk at the bottom of the pitcher. And then you add 3 cans of water, right? And you mix it up. Which has more orange stuff, that original can or the diluted pitcher? They're the same, right? Because all of the orange stuff that was in the can went into the pitcher. That's the solute. When you dilute the orange juice, you don't change the amount of orange flavor, pulp, sugar, all that stuff. That stays the same. All you're changing is the volume of the solution. You're adding water. And that's what dilution is. The amount of solute doesn't change, just the volume changes. So this is the equation that's very helpful for doing calculations. M1V1 equals M2V2. So that's a capital M, that's molarity, and V is volume. So M1 and V1 are the concentration and the volume of the same solution, number 1, whichever one you want to call number 1. M2 and V2 are the concentration and volume of solution number 2. And this equation works because the molarity, moles per liter, let me draw that. Where can I draw that? The molarity is moles per liter, and then when we multiply by volume in liters, we get moles. So the concentration of the first solution times its volume equals the number of moles of solute. When you dilute it, the concentration and the volume change, but the moles of solute do not change. So they're the same. So that's where that comes from. Very important. As people do this, drives me bananas. That equation applies only to dilution. You cannot use that for stoichiometry. Occasionally it will work, which is why some people do it, but many times it will not work and it'll get you into trouble. And this is an important lab safety note. When you're diluting acids, you always add the concentrated acid to the water. You never add water to concentrated acid. It generates a lot of heat and can cause the solution to actually boil. There was a stockroom accident at Fresno City College several years ago where a student worker forgot that basic principle and added water to concentrated acid in a large graduated cylinder. And it boiled and shot out of that like a cannon, and there was concentrated acid dripping off the ceiling. Thankfully, the student was wearing a lab coat and safety goggles and knew how to go use the safety shower. And he did get some chemical burns, but he was not scarred for life. He didn't lose his vision. He was fine. But it was a big mess, and hazmat came, and it was a big, big deal. Never add water to acid, always acid to water. So an example of dilution. How much 6 molar sodium nitrate solution should you use to make 0.585 liters of a 1.2 molar sodium nitrate solution? So it might help, we could make a graph just like we did, not a graph, a table, just like we did for the gas laws. We've got molarity and volume. So here's this first number we come across, 6.0 molar. So 6.0 moles per liter. Do we know the volume of that solution? No, we don't, because that's what it's asking us. And then there's a volume here and a concentration, 0.585 liters of this. Those two go together. You could call them one or you could call them two. It doesn't matter as long as you keep them together. So that's not what I want there. The concentration of the second one is 1.2 moles per liter. And the volume is 0.585 liters. And then this will be, we'll call that V1. So then our equation for dilution is M1V1 equals M2V2. We are solving for V2. I'm sorry, V1. We're looking for V1. So we're going to rearrange this equation, and we'll do that by dividing by M1. Because M1 over M1 cancels out. If we do it to one side, we have to do it to the other side. And there's our equation. So volume 1 equals molarity 2 times volume 2 divided by molarity 1. So this is 1.2 moles per liter times 0.585 liters divided by 6.0 moles per liter. This mole cancels that mole, this liter cancels that liter. We end up with the units of liters, which is good because we're trying to find a volume. We get 1.2 times 0.585 divided by 6. So 0.117 liters is the volume we should use. Is that a reasonable number? It has to be less than this. It has to be less than the volume of the diluted solution, right? And it is, so it's probably reasonable. Any questions? So that one we solved for V1. You might have to solve for M2. It's all the same idea. Here's an illustration of how we actually do that. This note that this is a salt solution. This is not an acid. So they're measuring out the amount of stock solution and then adding water to dilute to the total volume that's needed. You would use a different approach with an acid because you don't want to add water to a concentrated acid.